Alright, so I think some of you may benefit from an explanation of adding vectors, and in particular, the importance of asking yourself, what is the direction of acceleration? Why is that so important? Okay, so let's say you have a problem where on a frictionless surface, you're pulling a sled of mass m0 along the surface. Let's look at the forces. We have the force of gravity, we have tension. Okay, and we recognize if tension were to go to zero, if we let go of the rope, it doesn't fall through the ground, so we also have a normal force pushing upward. How strong is the normal force? As strong as it needs to be so that this doesn't fall through the surface. So if you push down on this, the normal force is going to go up. If you pull up on this, the normal force doesn't have to be as great. Now we add these forces together because we know the vector sum of the forces is equal to mass times acceleration. And so I can add these like vectors. And it doesn't mean we add these numbers. They're not scalars. You won't get the right answer. We need to add them like gravity plus the tension plus the normal force. If these are all the forces, when you add them together, you're going to get mass times acceleration. This is the resultant force. That's the net force, and that's mass times acceleration. But we asked ourselves this question, what is the direction of acceleration of this guy? And we know it's in this direction. You see the thing just speed up. So this can't be right. These have to add in a direction, in that direction. So we see, I made the normal force too big. If these are correct, I made the normal force too big, and now I can see, oh great, here's the normal force, and this is my net force. And that's equal to mass times acceleration. So you can calculate this out. You might use some trigonometry recognizing that this is a right triangle. You can find the net force and set that equal to mass times acceleration and solve for the acceleration. What if there's friction? Well, then you add a frictional force. And then you'd have to add that frictional force here. And you see, that causes the net force to be less. And you will then calculate a smaller acceleration. You could imagine a much stronger frictional force, in which case you'd say, oh wait, I'm not going to be able to move this guy. And so the total sum of the forces is zero, and we have a statics problem. Now there's another way to add these forces. You can do it Cartesian style. This is the same as saying the sum of the forces in the x direction equals mass times acceleration in the x direction. And the sum of the forces in the y direction equals mass times acceleration in the y direction. And because these are components, I don't need to put hats on them. These can be added like scalars. So how do we do that? Well, we have to pick a preferred direction. Let's call this x, and let's call this y. And then all we need to do is find all the components in the x and the y direction and set them equal to mass times acceleration. Well, this is easy. This is a y component. This is a y component. Ah, this is a hard one. It has a y component and an x component. And so I need to go here and separate the tension into horizontal tension and vertical tension. This is tension vertical, and that's the opposite side, hypotenuse, so this is the sine of theta. And this is going to be tension parallel, or tension in the x direction. Let's keep these consistent. Tension y, tension x, is equal to tension cosine theta. Now it's as easy as accounting. You just grab these guys and you put them all in the right category. The sum of the forces in the x direction, that's going to be tension x plus friction x, and friction is in the x direction, and that's the sum total. Let's see. Force of gravity, nope. Normal force, those are vertical. This is mass times acceleration in the x direction. Now for this problem it's easier because we don't have any friction. And so all we need to do is find the x component of the tension, and we have mass times acceleration. Nice. Now how how about the sum of the forces in the y direction are going to be equal to, that's going to be tension y plus force of gravity plus the normal force is equal to mass times acceleration in the y direction. And then we ask ourselves that question, even in Cartesian components. Are we in equilibrium? If not, what's the direction of acceleration? Okay, so for x, are we in equilibrium? Well, we think not. We have an unbalanced force in that direction. We're going to accelerate. So the acceleration is in the x direction, and it's good we pick this to be the positive direction. In the y direction, if you look at this in the y direction, it stays at the same height. So there's no velocity in the y direction in the beginning or the end. There's no change in velocity in the y direction. This is equal to 0. So these all add to 0. I forgot. Signs. I was a bad accountant. Let's take a look. This is the positive direction. So that means n is positive. That means the force of gravity is negative. And that means tension y is positive. So this is great. Now I can solve for the normal force. The normal force is equal to the force of gravity then minus tension in the y direction. We ask ourselves the question, does this make sense? Right? What this tells us, if there's no tension, the normal force pushing up is equal to the force of gravity pulling down. Not because they're Newton's third law pairs. It is because we are in equilibrium. But as we pull harder in the y direction, of course, the normal force is going to go down, just like as you pull the hair upward of a friend standing on a scale, you see the scale read less. So you can do it like this. We physicists find this beautiful, or I do. Or you can go the strict engineering style and take all the x components equal to mass times acceleration in the x direction and the y components, and you solve these simultaneous equations because they're linked by tension. So they depend on each other. Now, as beautiful as I find this to be, there are situations where you have 50 forces going in 50 directions. You could never solve them with trigonometry like this, with a drawing. You're just going to separate everything into its x, y, maybe z components, slam them into a computer, and it will solve all of those simultaneous equations for you. We take a look at another scenario. What if I pull harder and harder on this string? What's going to happen? The tension will get larger and larger until what ultimately happens? The normal force will go to 0. Okay, and this thing is gliding horizontally over the surface, not touching the ice. That's this scenario. You see the acceleration in this direction. This is our fuzzy dice, right? We only have two forces, the force of gravity and the tension. The normal force goes to 0. And it's crucially important again. What's the direction of acceleration? It's this direction, right? So I draw them so the net force goes in that direction. What happens if I pull harder? What happens if I pull harder? Then I can see the acceleration. You saw the acceleration to be kind of in this direction. How can I make the net force in this direction? It's just a matter of making the tension stronger. I pull harder on the tension, and then I see when I add the force of gravity to the tension, I get the net force, which is mass times acceleration. So this is the direction of the acceleration. And you can see, if I didn't demand that the acceleration be in this direction, that the total sum of the forces be in this direction, I would not be able to find the tension. You could also say, what happens if I pull it less hard, like this? At that moment, I let it go. The acceleration is in this direction. How does that happen? Well, the tension is less and less. And so the vector sum of the forces is downward, providing the acceleration downward. You can go to an extreme situation where the angle goes to 90 degrees, the tension goes to 0, and the sum of the forces is gravity. Not always, not down in here, but at the moment I let go. In summary, we want to recognize all the forces acting on a body. We want to recognize that they're vectors and add them properly like vectors. What a mess. We can add them graphically, or we can just take their Cartesian components and solve the simultaneous equations. But what's crucially important is we ask ourselves, what is the direction of acceleration? Because the resultant force must be in that direction. So if I see this thing accelerating straight, I better add the tension, make the tension strong enough so that when I add the force of gravity plus the tension, it comes out horizontal.